Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. The more I look, the more times I encounter time series problems in need of a forecast. Today on the show, I speak with Georgia Papacharalampous about the paper Probabilistic Water Demand Forecasting Using Quantile Regression Algorithms. We discuss stream flow forecasting and the quantile regression technique.
Hello, I am Georgia Papacharalampous and I am currently a researcher at the National Technical University of Athens in Greece.
Well, thanks for coming on the show today. I'd love it if you could tell me a little bit more about your research. What sort of fields and questions are you interested in?
Most of my research is in statistical hydrology, and I really like machine learning, statistical learning, data science approaches.
Absolutely. What is hydrology?
Hydrology involves the study of several variables, for example, rainfall, river flow, and variables like this, and also the study of their properties, and also forecasting, river flow forecasting, rainfall forecasting, and also other things like simulation of the same variables.
So I have known a few people who have a little water meter in their yard. It's kind of like a graduated cylinder, and when it rains, they'll go out and see from that how much rain there was. I'm not sure if that's the most accurate scientific instrumentation. I'm curious, where do you get your data from?
Well, actually, from global datasets mostly, which are open, and they have a lot of stations and long enough records for doing a lot of cool stuff.
Well, when I think about rainfall, the obvious thing is, how many inches or centimeters of water came down in a particular period of time. What are metrics on rivers? What kind of interesting statistics do you gather?
I would say that we would particularly interested in river flow forecasting because we might want to do flood forecasting, which is important because we need to protect ourselves and our homes and etc. from such disasters. And also for operating reservoirs and for other operational purposes.
When it comes to doing a forecast of something like a flood, or to make a comparison, earthquakes are almost impossible to predict, I'm told. Something is missing. They don't know how to do it. I'm curious about what goes into the prediction of a flood. Is it just historical time series data, or are there environmental factors you study?
I think what I could say about that is that the uncertainty is of course higher when we need to forecast such types of disasters and when we care more about extremes. And in this case, maybe even in the statistical learning fields, the advancements, only recently there are some advancements towards this direction. But I don't really know because my own research is not that much about that. I mostly focus on monthly stream flow forecasting, on annual stream flow forecasting, and sometimes daily stream flow forecasting, also probabilistic forecasting, using models such as the models that are in the paper.
Right, so I primarily invited you on to talk about probabilistic water demand forecasting using quantile regression algorithms. Maybe a good place to start would be with the quantile regression algorithms themselves. For listeners who aren't familiar with the technique, could you describe what it is?
Quantile regression algorithms is a whole family. There's a whole family of such algorithms. Are algorithms that are regression algorithms that deviate from the standard regression algorithms in the sense that the focus here is placed on the quantiles and not on the mean. Actually, when we solve a typical regression problem, then the algorithm needs to learn how the mean of the response variable changes with the changes of the predictor variables. And in this case, the algorithm is told to focus on the mean by using, for example, the R-square error objective function or some other similarly conceptualized error function. But in a case that, for instance, we would like to focus to know which will be this urban water demand forecasting value for one day, for one specific day, that will be exceeded with probability, let's say 10%. Then the algorithm needs to learn how the quantile of urban water demand of level 0.19 will change with the changes of the predictor variables. And that can be done by using a specific loss function, which is the quantile score, also known as the pinball loss.
Would you mind giving examples of some of the predictor variables?
Actually, in the paper, we used 52 predictors. Some of the predictors were endogenous predictors. That means average urban water flow at some preceding days. Here we used the day before up to 7 days before the forecast. Also, high temperature at several days, average temperature, low temperature, high dew point, average dew point, low dew point, high humidity, average humidity, low humidity, high wind speed, average wind speed, low wind speed, high pressure variables, low pressure variables, and total precipitation variables at several days before the forecast.
Makes sense. And I'm curious, do you have to do any fine-tuning or feature engineering of that, or can you just take the raw observational data and use it directly?
We did not do variable selection. We selected a priori these variables and used them because we have two algorithms, some algorithms, the boosting algorithms and the generalized random forest algorithms that are robust in redundant predictors. So we didn't have to select variables.
Well, once you're, getting to the point where we can frame it as a machine learning problem, what's the exact objective variable you want to study?
It's urban water demand in the next day.
Well, let's maybe dive into some of the results. Tell me a little bit about how the model performs given the factors we just discussed.
The best model here was found to be the linear boosting algorithm alone, and also two combiners that were tried, the mean and the median combiners, were found also to be skillful. Now, the linear boosting algorithm was the best one, probably because of some shifts and trends present in the time series. And simple combination methodologies are known in general to perform well. Here they performed better than the linear boosting algorithm, only in one, if I remember correct, in one quantile, in one level of predictive quantiles. And that must be related to the particularities of the problem. For example, in other problems, they're found to work better than the individual algorithms in most cases.
And as you're training your model, what sort of metrics are you looking at? I know accuracy and F1 score are popular things. What's appropriate for your project?
Here we used the quantile score because this is a consistent score for this problem. Actually, the thing is that we need to match the scoring function to the forecasting task. And here the quantile loss function is a consistent function for that. Other possibilities could be the interval score, for example, or maybe there are other scores for that. But we used a quantile loss function.
And in terms of performance, how well does the model do?
It performs better than the remaining algorithms. For the previous question, maybe I should have also said that this is a probabilistic forecasting problem. So quantile score is also appropriate for this reason too.
Oh, good point. Can you expand upon that? I know many listeners will be familiar with pretty basic classification problems where you're making a Boolean prediction or maybe a forecast where you just give one singular valued number if you think the stock price will be this much money tomorrow. What does a probabilistic forecast do?
Actually, even probabilistic forecasts can come in some different forms. For example, we can give the entire probability distribution, which is not the case here, and we can give quantile forecasts. This means forecasts for specific quantile levels. That is the case here. Even in the case of these algorithms, the quantile regression algorithms, we can produce many quantile forecasts for many quantile levels and then have something close to a probability distribution.
Well, that gives us a much more robust result, I guess, at the end. I don't just get some point estimates. I can look at the quantiles, and if I'm, someone from the government that needs to make a decision about what action to take, I'll get a richer, informed forecast. Is that part of the idea?
I would say that it's not only about giving the best guess forecast, which is also important, but also giving an idea of how far the true value can be from the best guess forecast that we provide, and that could help decisions. The same example as before, maybe somebody needs to know also what is that urban water demand value, that daily urban water demand value that will not be exceeded with a specific probability.
Do you have a vision for who some of those decision makers are? Would you like it if, politicians were looking at your work, or is it farmers? Who can get the most benefit?
I think that they're the people, that the managers in the authorities that take the decision about how to manage and how to operate the water treatment and the water treatment plants and wells, because these people will need to know every day for this day and the next day what will be the demand, so they can cover it. But of course, quantile regression algorithms can be also used for other temporal scales and for other horizons. So maybe also long-term forecasting could be a possibility with them, or medium range forecasting. Although in the paper we had short-term forecasting.
Yeah, the use of the quantile forecasting is very interesting to me, especially in a problem like this. I feel like it gives you a much more robust description of your environment, more useful for making inferences with. But I also have to say, it's not a common technique I see coming up a lot in forecasting. Can you tell me a little bit about the inspiration to apply that methodology?
The thing is that we need to quantify predictive uncertainty. We need to provide probabilistic forecasts. So instead of using a typical regression algorithm, for example, neural networks, we use quantile regression neural networks that are neural networks using a different loss function. Not, for example, the least square error function, but the quantile loss error function.
If you're looking to progress into a well-paid, fulfilling career in data science and machine learning this year, Springboard's 6-month data science bootcamp is built on human support and backed by their job guarantee. It's 100% online and on your schedule, with over 500 hours of structured data science and machine learning content, and most of your time is dedicated to hands-on work for a portfolio that will stand out to hiring managers. You're paired with an experienced industry mentor that will meet with you one-on-one every week for technical and career guidance. You'll also have your own career coach guiding you through the job search with behavioral and technical mock interviews, networking training, and more. Springboard's data science graduates average an increase in salary of almost $24,000 a year, and they've been hired by the likes of Facebook, Apple, and Google. Their job guarantee also means that if you don't land a job within 6 months of graduating, they'll fully refund your tuition. Visit springboard.com and use the promo code DATASKEPTIC, all one word, to receive a $750 discount. That's springboard.com, promo code DATASKEPTIC. Well, we talked about some of the features you're using, things like temperature and yesterday's rainfall and a lot of atmospheric measurements. I'm curious if there's any data set or any types of observations you think could improve the process that are maybe missing. I don't know if there's some variable you wish you have that isn't available.
Maybe considering holidays in some way, maybe that could provide some improvements. And in the paper, there are a lot of hydrometeorological variables, so I don't think of any particular hydrometeorological variable that could be added.
Gotcha. But the holiday is an interesting one because it sort of implies the presence of human behavior, that we're going to change the way we operate. I don't know if most listeners will have had a chance to look at urban water use demand data before. Can you give a rough description of it? Does it have predictable trends and cycles when you look at it?
Actually, one needs to consider several periodicities. That can be the weekly periodicity that we had to consider here, also the daily periodicity and the annual periodicity.
Can you tell me a little bit about how you implemented this from a coding perspective?
The greatest part of the algorithms was already available in our packages, and there was an additional degree of automation which was required. Actually, for quantile regression, it was QuantReg, the QuantReg package. For linear boosting, the MBoost. For generalized random forest, the GRF package. For gradient boosting machine, the GBM. And for quantile regression neural networks, it was QRNN. Now, there was an additional degree of automation required for considering many levels of predictive quantiles, actually the 5 levels of predictive quantiles that were considered for the paper. And also then we had for some of them the experiments, the problem of quantile crossing, so we had to consider this problem too. And of course, the building of the regression matrix, which is common for all algorithms, for all regression algorithms. And at the end, of course, for the combination methodologies, we have to combine the results of the individual algorithms. So use all the R packages together.
Very cool. And were you an experienced R user beforehand, or was this your first big R project?
Actually, we have used the same algorithms before. We have used them for river flow forecasting, prediction, and forecasting through post-processing. Now, this means that we had used conceptual hydrological models, which are some models that they are used for prediction, but they are also used to describe the catchment's behavior as a whole and describe hydrological phenomena. So there are some certain models that are in particular of interest to hydrologists. And we applied quantile regression algorithms for improving the performances, but most importantly for converting them into probabilistic forecasts, because these models provide only point forecasts.
Well, the paper presents the framework for probabilistic urban water demand forecasting. I'm curious where you see the future of that framework going. Is there more to be done with it, or maybe other people start adopting the same approaches? What do you think is coming next?
I think this is an approach that is directly applicable, and I think it is very straightforward also in comparison to other approaches that have started to appear in the literature, because probabilistic urban water demand forecasting is rather a new problem, and I think there is much future here.
Very exciting then. Is this your main area of research, or are you working on other things?
I'm mostly working on hydrology and statistical hydrology. This was a part of a project that I participated half a year before, and this was the outcome of my work there.
Do you have any thoughts on where further investment should go? Are there maybe ways in which this could become commercialized or some sort of open source system? It seems like it's ready for prime time, perhaps. Just curious about how decision makers might be able to leverage the work.
I don't know, but I think that the most difficult step before applying the algorithms is maintaining a data set for that. So I think that these algorithms are directly applicable, and it's like applying typical regression algorithms, like applying random forest. And I think emphasis should first be placed on maintaining the data set at the form that it should be. And then I think it's something directly applicable.
And lastly, you'd mentioned that this is becoming more important. What's driving that need?
It's again because people should understand that we should accompany our best guess with also probabilistic forecasts. For example, with quantile forecasts to improve management and operation.
I'm sure uncertainty plays a big role in this because the demand is inherently kind of unpredictable, at least not precisely. Can you talk a little bit about how you account for uncertainty in the work?
The answer is by using quantile regression algorithms. This is a family of algorithms that can provide probabilistic predictions. Actually, it can provide quantile predictions. So it is a direct and straightforward approach to probabilistic forecasting. And in the case of quantile regression algorithms, because they can provide the predictive quantiles and not the entire probability distribution, if somebody needs to have a picture of the entire distribution, then he has to predict the quantiles at several levels, not just one or two quantiles.
Can you talk a little bit about what you used? How many quantiles and why did you pick the number you chose?
It was actually 5 quantiles. The quantile of level 2.5%, 10%, 50%, which is the median, the 90%, and 97%, which are actually the quantiles that define the 80% prediction intervals and 95% prediction intervals, and again the median. And the reason why we selected these quantiles, because those quantiles that appear in the literature a lot, and maybe the reason behind that is because they are mostly of interest to the managers to make the decision.
So if I ask you to generate a new forecast for me for tomorrow, what does the deliverable look like?
For the case of the paper, it was 5 values. One can have as many values as he wants if he defines the quantile levels while training.
And you'd mentioned making that prediction at one location. Are you able to forecast for like a large mesh of different points?
Yes, but the algorithms are trained separately for the station. So we have to train them and then we can get the forecasts for each station. For as many quantiles as we want, but they have to be trained appropriately because the training is made separately for each quantile. And also, I think that this is an important point because these approaches can be fully automatic and they can be applied to large datasets. And also, the computational requirements are affordable. So this is another reason why they can be applied for operational purposes. And also for this work, we applied them for 54 stations and also for performing forecasting for many days. That means one day ahead, but for many experiments, like 500, let's say 500 experiments for each station. And that took for all algorithms together less than an hour.
Gotcha, pretty scalable then.
I think it's affordable for operational purposes because let's say if we had 1,000 of stations, it would take less than a minute for one day ahead. Of course, the best thing is to train them again every day, and that means that you have to maintain a good data set in the proper form to clean the data because, for example, for the city of Patras, the data recorded at a frequency of 1 minute, and you have to convert this data to the daily scale, and you probably have to clean it because measurements have several problems like missing values or missing dates.
Yeah, a lot to be managed on the data side for sure.
And I think another thing that is rather important here, and it is important for all problems that involve algorithms in general, is that we need to assess them first in big data set before applying them in practice, in operational context, etc. And the reason behind this is that if we only apply them in a single time series and find, for example, that they work well, we might be mistaken. For example, there is the no-freelance theorem, which tells us that among a pool of algorithms, there is no way to know which of them will perform well for one particular problem. And that means that the results of case study are not generalizable in general. So if we want to make a proper assessment, we have to use big data sets.
Well, when you think about the long term and where this work is going, I'm curious where you hope your research will have the most impact.
Maybe for improving the operation of, treatment plants and wells, maybe managers. If they have such forecasting probabilistic in such quantile forecasts, then they can operate the treatment plants and wells more appropriately. I think this is something directly applicable actually because it's as typical. These algorithms operate like typical regression algorithms. It's a very straightforward process to apply them. You just have to build the regression matrix and define the variables and build the matrix, and then you train the algorithm, you get the results. If you have made the proper assessment, you can find which algorithm performs better, and then you can use this algorithm to gain some improvements over the others. I hope that it will be used for the operation of the water distribution network of the city of Patras and of other cities.
Georgia, is there anywhere people can follow your work online?
I have a Twitter. It is Georgia Papachar.
I'll have your Twitter in the show notes so people can follow you. Thank you so much for taking the time to come on Data Skeptic.
That concludes another installment of Data Skeptic Time Series. Our guest today, Georgia Papacharalampous. Thanks to our sponsor, Springboard. Myself, Claudia Armbruster, as associate producer, Vanessa Bly, guest coordinator, and our host, Kyle Polich.